So today we're going to talk about radioactivity, a bit of an introduction, a bit of a history, recap some of the things you hopefully remember, and deal with in terms of various parts of it. And we'll look at a bit of E equals mc squared as why radioactivity can happen. So this first bit, all about history, not going to come up in an A level, so hopefully you can enjoy. So when we think about radioactivity, the story surrounding it really starts with something that isn't about radioactivity at all. And it starts with this chap who is called Wilhelm Röntgen. And Wilhelm Röntgen in 1895, I think, discovers X-rays. And the discovery of X-rays is a huge thing. Now, X-rays are produced in a thing called a cathode ray tube. The cathode ray tube is essentially a lot like the electron gun we saw with wave-particle duality. So you have a vacuated tube, and you have a accelerating voltage plate, so positive. You get thermionic emission, so you get some electrons that pop out. And they were called cathode rays because something that they were able to study was that by setting this up, you generated some sort of rays that would go across, and they would call cathode rays. Now nowadays we know that essentially a cathode ray is a beam of electrons, but you can get these electrons to go at very, very, very high speeds, carrying a fairly large amount of kinetic energy. And X-rays were generated by Röntgen by smashing them into a target. So he picked a sort of metallic target. So there's some kind of target, and when these cathode rays sort of strike them, what would happen is the kinetic energy of the electrons would lead to a sort of a process of like making gaps in energy transfers in other atoms, which we'll look at. We talk formally about X-ray production, but what we would get is a series of rays coming up. I'm going to do a rainbow pen for this. You'd get X-rays emitted. So you've got high energy electrons striking the metal target, X-rays come off, and that's still how we generate X-rays generally today with this kind of methodology. And it's quite nice because you can alter the potential difference here, and that can alter the energy of the X-rays that you get to generate. Now, Röntgen discovered this, as like with many people at this time, with utter accidents. What he created was a rather sort of fetching tube, because he knew that cathode rays could cause scintillation. You could make various things glow, and so what he had was, going to clean this up a little bit. He basically built a little window, so surrounding the whole device, so a window for the X-rays for things to come out of, and he was deciding that he was going to try and put something here to see the effect of these X-rays on this screen. And the idea is the screen would glow. But in making it, what he noticed is that the screen that was nowhere near his hole, over here, was actually glowing. And that's because the X-rays were actually traveling through the exterior of his tube and causing scintillation. So there's this study at the time of things that generally just glow or darken photographic film and so on and so forth. Now, this picture here is commonly thought of as being the world's first X-ray. That's of his wife's hand, and that's her wedding ring there. But Röntgen actually did it himself accidentally when he had the screen set up. So he had his sort of screen set up in front of his tube, and he walked in front of it. So he sort of like stood in front of it, he stood in front of the tube, and there was a shadow formed on the screen. And that was sort of the first image of him seeing himself. Now, it takes him 6 weeks from seeing this to then building this to see his wife's hand before he publishes it, because he's genuinely afraid that he's sort of describing invisible light. He shouldn't necessarily have been, but it's high energy invisible light. At that point in the EM spectrum, what is known about are, we know about visible light Herschel discovers infrared radiation in 1800, and just a year later, ultraviolet radiation is discovered. And they know about essentially radio waves, sort of which become radio waves and microwaves in the 1880s from Hertz. But this idea of this sort of high energy stuff is a mystery, and they don't know about it, and so he's genuinely a little bit perplexed by it. But in doing so, what he sets off, and when he publishes, he sets up this huge amount of research that gets done into invisible rays. And the next person who comes onto the scene is this guy. And this guy is Henri Becquerel. Oop, I've deleted that. I don't know what I meant to do. And his discovery is only a year later, 1896. Now, his discovery is largely spurred on by the discoveries outlined by Röntgen, because everyone's trying to investigate these X-rays as they've become known. This idea of invisible radiation given off by things. And Becquerel is studying materials that are phosphorescent. So he's studying materials that basically like your glow-in-the-dark stars, if you glow-in-the-dark stickers, that absorb light and then re-emit it slowly. So you get certain things like fluorescence, which is where a fluorescent tube, for example, will glow, but when you turn off the electricity, it'll stop glowing again almost immediately. Whereas these materials release their energy slowly. And so what he did is he decided to do a bit of an experiment where he took some materials, and one of these turned out to be a uranium salt. But he would take a phosphorescent material, and he was trying to see whether these things would give off X-rays. And the way he would do that is by sealing some photographic film inside a container, putting the sort of salt on top, exposing it to a large amount of sunlight, and then seeing if it's developed. And the idea being is that what he's thinking is that the salt will absorb some energy, then it will re-emit those things by visible light, and that some of that energy will be enough to get through and to darken the photographic film. Now, he does this with a uranium salt, with pitch blende, and he finds that it's darkened. He finds this down here, having sent in. But what he notices, largely due to a bit of luck, is that happened to samples that had not been exposed to the sun. So he repeated his experiment and repeated his investigations, but without the sun being a sort of a driving force. And what he was able to recognize from that is that something was just naturally coming out of this uranium salt. There was some kind of natural radiation that was coming out and was darkening the photographic film. So these things were like X-rays, but they weren't being generated by a cathode ray tube. They weren't being spurred on by the creation of the sun. There was something. So there's something in uranium salts that emit radiation. Now, I'm going to put that in because that term doesn't exist at the moment. That's not invented until Curie's turn up. And this is his sort of like shadow. You've got this is sort of a Maltese cross. So you put a metal plate underneath one of the salts to show that it was passing through paper, but not through metal. And he starts doing investigations of these things. And very quickly he realizes it's got nothing to do with the glow-in-the-dark tendencies of these things at all. It's something from within the uranium salt. And so Becquerel publishes his work, and he doesn't, these radiations, they're not named Beccarays as he tries to get them called, but he publishes sort of this. So 1896, you've got Henri Becquerel identifying that something is coming out of these rocks, and it's got nothing to do with the sun. Now, the next kind of people that turn up the people that are sort of very commonly thought of as being related to radioactivity, and that would be Marie and Pierre Curie. And they were two scientists working in France. And the original person doing the research was Marie Curie. Pierre eventually, he quite quickly worked out that stuff she was working on was much more interesting, so started working sort of with her. So what he has done, what Pierre did in sort of the 1880s. So what they've done in around about the 1880s, Pierre has invented a device called the electrometer. And what that's able to do is it's a really sensitive way of measuring charge. Now, what they didn't know at the time, but obviously we might know, is that radioactive radiations at alpha, beta, gamma, alpha and beta particles are charged themselves, but they all create ions because of their ionizing power. So what you get from this is you do get charge being detected around radioactive substances. And so what he was doing was that she, so she first studied and she found this sort of like this uranium pitch blend. And what she found is that if you had, if you had a sort of uranium rock, it turned out that the air around it was able to conduct electricity. So if you sort of had plus and minus, you could get an electric current running through the air over very small distances. But what that meant is that your air is ionized, or it's sort of there are free free charges are free in the air, which will allow the air to conduct electricity. Now, air doesn't normally conduct electricity unless you've got something like a lightning bolt or giant voltages to create sparks. There was nothing there, so what they did was generate this. So what she then did was she worked to try and isolate the material that's inside here to try and work out, well, what is causing this? And in doing so, the pair of them went on to isolate several new, previously unknown elements. Now, the first, because it's uranium salt, the first thing that's kind of obvious is they found this one. They found uranium. Okay, so they isolate the uranium from the uranium salts, and they say, which people already knew about uranium, but they find that uranium causes this effect. So there is something that's being given off by uranium which has this thing. But as they worked out, the uranium that was in the uranium salt, so once if you had your sort of pitch blend and you purify it and you pull out all the uranium, well, this doesn't account for the amount of charge. That you're detecting in the air. So whatever the uranium is doing, yes, it's doing this, but it's by no means doing it enough to give you this result. So whatever is in here, there must be something aside from uranium inside this ore that is leading to this effect. And actually what then turned out is that it turned out that uranium, sort of gram for gram, was not the most radioactive substance that's in here. Like, what's in here are other elements that are contributing a great deal more to this problem. Now, so the Curies isolate two sort of new elements, okay, and they do that via first things. Now, the first one that's kind of easy to identify is polonium, which is the first one that's isolated, the first one that's named. It's here on the periodic table. And it is isolated and explained quite easily because it has a chemical similarity, and this is where the periodic table doesn't quite necessarily go vertical. It's quite similar to bismuth, and that's because they both form part of what's called the metalloid staircase, where they're kind of this crossing the boundary between metals and non-metals. But there's no bismuth in this thing, so it was quite easy because you just went looking for the bismuth-like substance, and you knew it wasn't bismuth because there's no bismuth in here. So polonium was really easy to identify. It's called polonium. It was named after named after Poland, which is where she is, and that's identified in 1898. And so sort of Curie starts filling in bits of the periodic table. Now the other one that is over here, well, this is radium. Now, radium turns out hugely radioactive. Now, it's named, this is where Curie does coin the term radioactivity. It's around this time. And the term radium is named because it's giving off a lot of these rays. It's like the most ray creating thing. So they've called it radioactivity, and radium gets its name from that, which is weird because uranium and polonium are both known about and identified first. But this unknown element, which they know is there, they know it exists, and they know it accounts for a large amount of it because it's the one that is responsible. They call it radium for radioactivity. Now, so what they were trying to do is that radium itself would never be isolated really until I think about 1910. The first time she would actually properly as a singular thing, she would eventually get it as she would get some radium chloride. So she would not really, she would get radium chloride. Would be sort of like separated out in 1902, and the amount of radium chloride she was able to get, she took 1,000 kilograms, so million grams of the ore, and from that she managed to get 0.1 grams of radium chloride. So that would be, my guess is RaCl2. Yeah. So of radium chloride. Now, why was it so hard to find? Well, A, it's in there in minute quantities. But the other big problem that they had is that radium, this is on this part of the periodic table, radium behaves a lot like barium. And there's quite a lot of barium already inside this ore. So to chemically separate two things that are very, very, very similar, not even knowing that there's very little radium inside it. I mean, she at first was sort of like, crushing up, say, 100 grams of the stuff, in a rather sort of optimistic way, but she needs a ton of it just to get 0.1 grams of radium chloride. And that knowledge is bonkers because that was still accounting for huge amounts of the radioactivity of the overall ore was coming from this tiny, tiny fraction of radium chloride. So that was kind of the work that they were doing. Now, they didn't. One of the other interesting things is that she does recognize something quite amazing, which is that she recognizes that tumor cells are killed when placed next to these radium sources. So she is the first person, essentially, to recognize the possibility of radiotherapy. The healing element, the healing aspect of killing tumor cells by putting them next to radioactive materials. Now, she wouldn't, because people didn't know at the time, they didn't know that obviously these things can cause these cancer cells as well, because they're not hugely understood. this is still 50 odd years out from the discovery of DNA. So, there isn't, so what they are just aware of is that you can kill things by being next to it. And that led to a huge sort of cottage industry on things that, you could go and bathe in the healing water that had been enriched with radium salts in baths in Paris and stuff. Quite dangerous, not very nice. So the Curies are very responsible for isolating these things, and it's a huge, huge effort to do. And she wins 2 Nobel Prizes. He dies in the sort of, I think, around 1910ish, because he gets killed by a horse and cart, I think. Gets run over. She eventually will die as partly in 1906. He passes away. She would eventually become ill as a result of her exposure to all this radioactivity. But equally, there would be, some part of it would have that impact. Now, yes, so she died in 1934. So the next sort of like group of people on the scene are these two. And this is Ernest Rutherford. And this is Paul Villard. And these two gentlemen are responsible for the alpha, beta, gamma stuff. So Rutherford, he's at the University of Manchester, and he starts studying the nature of the things that are coming out. So he starts isolating pure samples and investigating what's coming out. And what he does is he does 2 sort of experiments. One is the classic one that you will probably hopefully remember from Radioactivity in year 11, is the idea of you hold your source and you see whether it gets through different shields. So paper, paper, aluminium, lead, see what things get through. Make them not just sort of like putting one down, but making them of different thicknesses to see their absorption stuff. And there's different properties that he sees, which is that sort of when you emit alpha, from something, when you emit an alpha particle, you get to a sort of certain thickness of your paper, and they just stop being able to get through. So which kind of tells you they've all starting from the same energy, because you get to a sudden thickness, and suddenly you would detect. So if you've got your sort of number of detections against your thickness, you sort of it comes along, you detect them all, then suddenly you cross a line and you sort of drop down to 0. So alpha particles are coming out with all the same energy. He calls them alpha. Beta, he finds out that when you throw them through a metal sheet, what happens is that they get stopped, but there's a sort of an exponential decay of the number of detections you've got against the thickness of the plate that you're sending through. So the beta particles are coming out with lots of different energies. And then you've got gamma, which is not isolated by Rutherford, but is identified by Paul Villard. But Rutherford would call it gamma because he would have named alpha, he'd named beta, and he then said, okay, this is the third type, I'm going to go with gamma. Now, the other way in which these were identified was by throwing them through a magnetic field. And this is something you hopefully seeing in electromagnetism, is that if you've got a charged particle, you can deflect them either with a magnetic field or an electric field. But what we'll see is that alpha will go in one way, beta goes another way, which tells you that alpha is positively charged, beta is negatively charged. Gamma goes straight through, tells you it's got no charge at all. But also the radius of the curvature. Beta has a different curvature to alpha, and this curvature of alpha is a lot less because it's more massive. So he realizes that there's a sort of force equals mass times acceleration. If you're trying to make something move in a circle, you've got force equals m times v squared over r. If you've got a bigger, so the radius of your curvature and your mass kind of have that relationship, because for an alpha particle, although you've got more charge, plus 2 rather than plus 6, plus 1, minus 1, it's so much more massive, it's just much harder for a certain force to make it deflect. Beta deflects on a much curve, gamma goes straight through, so we get our sort of common thing of alpha, beta, gamma. And we get our ideas of the mass, which is 4, 0, 0, and the charge, which in terms of things is +2, -1, 0. And that is the sort of thing that that's what Rutherford and Villard sort of identify and say, oh, there's only these 3 types. There are more. Well, turns out there is slightly more. Because the last person I kind of want to talk about these two, and I want to finish this because this is Marie Curie's daughter, Irene. It's Irene Joliot-Curie. That's her husband, who was also awarded the Nobel Prize in Chemistry in 1935, a year after Marie Curie had died, because they actually were the people in the 1930s who identified that there was another type of beta. There was this common beta, the beta minus particle, which did this trick, but there was an identical particle that went the other way. They found the positron. Which is the other one you kind of need to know about. Still got a mass of 0, got +1. They were the first people to isolate and identify the positron as being the opposite of a beta particle, and were therefore discovered the concept of antimatter, which is kind of exciting. And so this is a bit of a history on radioactivity. We'll summarize sort of the rules and various things, but what we'll do in the next video is to sort of have a bit of a insight into why does radioactivity happen from the point of view of E = mc².